Hello friends, I am Shashank Sekhar from Department of Geology, University of Delhi. Right now we will discuss about assessment of groundwater quality. So the topic for the day is assessment of GW, that is groundwater quality. Now let's see what we will discuss here. We will understand the fundamentals of groundwater quality. What makes a groundwater quality? Know about the parameters. Then understand the differences between contamination and pollution of groundwater. Once we understand this, then we will examine utility of groundwater for irrigation purpose, for drinking purposes. Not only that, then we will learn about graphical representation of water quality data. Okay, water is a basic life supporting system. World over, people depend on it. Nowadays, dependence on groundwater has increased tremendously. We use it for drinking, we use it for irrigation, we use it for other industrial uses. Look, if we use it for so many purposes, we must know the quality. What do you think? Is that water which you get in subsurface as a groundwater is pristine? No, no way, no way. It has a baseline concentration. And what is that baseline concentration? It dissolves the solids when it moves subsurface. And then that must be below desirable limit for the desired use. Besides, you will have bacteriological contaminants there. You might have radioactive substances, and there could be many other things because water is a universal solvent. So when we talk of water quality, we have to take care of all these things. Now let's understand. What is water quality? What do you mean by quality? Quality of life? Then what defines quality of life? Money or the pleasure time or the leisure time? There are certain parameters. Similarly, in water quality, we have physical parameters or organoleptic and physical parameters. We have chemical parameters, we have bacteriological parameters, we have radiogenic substances. All of them adds to the baseline concentration. Hang on, that's not all. Quality depends on the desired use of the water. Let's say, if I want to use this water for drinking purpose, then the quality will be different. The parameters assessed will be different. I want to use this for irrigation purpose. The parameters assessed will be much different than what we do for drinking purposes. So water quality depends on the desired use. Once we take this in our mind, we will evaluate the parameters for desired use further in the text. Now we must understand two things: pollution and contamination. These are really words which you must be listening a lot. Pollution and contamination. Very often they are used synonymously, but there is a subtle difference. And to be more scientific, most of us talk of pollution as an anthropogenic source, that is human-induced source. But contamination is taken as a geogenic source. Let's look at the literary meaning because most of us are not very clear where and how to use this. What contaminate means? Contaminate means to add something which may be not desirable, which may be dangerous, but to add something. And you also say you have contaminated my mind. You have added something to my mind which was not desirable. But it never says in the literary meaning beyond a limit. Pollute literally means adding something to water, air, or land which is beyond the desired use. If we go by this, then contamination can be both geogenic or anthropogenic. Geogenic means human induced, while anthropogenic, no. That's not the way. Many of you will confuse. It's the other way around. Anthropogenic is human induced and geogenic is nature induced. Be it so. Then what is pollution? The movement, contamination from either geogenic sources or anthropogenic sources crosses the desired level, that is pollution. We finish this here because many books, many workers follow different perspective and definitions, but in my perspective, this is okay. Next, how do you measure quality parameters and how you report them? As far as measurement is concerned, there are protocols defined by different institutions and agencies. The first of them is WHO, that is World Health Organization. It sets the protocols which has to be followed by laboratories. In tune to that, each country has its own Bureau of Standard. In India, we have Bureau of Indian Standard. It defines the protocol for measurement of what? Organoleptic and physical parameters, chemical parameters, bacteriological parameters, and radioactive substances. More important, as a hydrogeologist working in groundwater field to us, is how the lab reports it. Most of the labs, they report this chemical parameter in terms of milligram per liter. For minor constituents, even for trace elements, sometimes they use microgram per liter. Now, we must be aware that 1 milligram per liter is approximately equal to 1 ppm. 1 milligram per liter is approximately equal to 1 ppm. Now that's an approximate relationship. We must keep in mind. It's not the sensu stricto true relationship. In groundwater chemistry, when we do some analysis and understanding, something more important is there. That is milli-equivalents per liter. And what is that? ppm or milligram per liter divided by equivalent weight. Now, what is equivalent weight? That must be a question in your mind. And that is nothing. Formula way divided by charge of the ion. So we understand reporting of chemical parameters. Now, with respect to organoleptic and physical parameters like color, we have Hagen units. It quantifies the color and then that's matched to a set of the standards and you get a numeric value. And then you say, okay, that's acceptable. It's not acceptable. Then we have turbidity, you have NTU. NTU is nothing, a scattering of light vis-a-vis incident beam is observed at 90-degree angle and it is quantified. For order, for test, you have agreeability. How you agree to that? It's agreeable to me or not. If it's agreeable to me, that's good. So it's an accepted order, it's an accepted test. And then we have pH. All of us are aware. What is pH? Negative logarithm to base 10 of hydrogen ion concentration in moles per liter. Hang on, it's not over yet. You have bacteriological parameters, and then it says, standard says that there should be none detectable in 100 ml of sample. For radioactive substances, the reporting which has to be done is in becquerels per liter. So we understand how they are measured and how they are reported. Okay, now we come to the topic, quality criteria for potable water. Now what is potable water? The one which you use in house for your drinking purposes. See, this is the most important part of water quality. World Health Organization, WHO, has worked out in details. These are the parameters which needs to be assessed. These are the desirable, these are the permissible limits. It's an exhaustive list. If you go and memorize it, that will take days. It's not advisable. You must be aware that these parameters are there and they can be accessed through web link or through a published literature. In tune to that, Bureau of Indian Standard, that is BIS, it has its own parameters. You will ask me why there are two different parameters. Because the socio-economic and geographic conditions vary, and so each country or a region has freedom to adopt its own parameter. And thus in India we have Bureau of Indian Standard, BIS, which has an exhaustive list of parameters. As we discussed earlier, they are for organoleptic and physical parameters, for chemical parameters, for pesticides, for radioactive substances, for bacteriological parameters. It is available at a cost from Bureau of Indian Standard. As a student, you might be wondering, why should I pay for this? Okay, hang on, don't worry. Google, you will find that in many other secondary sources available on website like at cgwb.gov.in, they have that in one or other form. The more important thing when we talk of water quality for drinking purposes is how the pollutants affect different parts of the body. Let's have a look at the figure. Look at the figure, what the title says. Adverse effects on human body due to pollution of drinking water with respect to a few parameters. This is not exhaustive. There are only few parameters. Don't worry, this is a naked body. This is for teaching purpose. Boron, what it does? It affects the nervous system. What mercury does? It affects the brain and nervous system. Chloride, together with sodium, increases blood pressure. So you must be listening that you must lower the sodium and chloride intake to reduce your blood pressure. Lead, it hinders physical and mental growth of children, causes anemia and damages kidney. Lead poisoning is one of the most common types of poisoning. Nitrate, the very famous blue baby syndrome. What these pesticides do? They're a lot harmful. They cause cancer, they damage the nervous system, they damage your reproductive system, they severely damage the immune system of body. On the other side, you have fluoride. It harms your teeth, and there is a fluoride at the bottom. It causes fluorosis, it deforms bones and gives problem to joints. Let's look at sodium. It causes damage to people who are having heart disease. Iron, it gives a stomach disorder. Cadmium, it again has adverse effects on bones and sometimes it also causes cancer. Sulfate together with magnesium causes diarrhea. And the famous arsenic, it gives rise to cancer, mostly cancer of skins and a lot of other related issues. So we must be aware that these pollutants should be avoided in drinking water. Okay, let's move ahead. We talked of potable water. Now we'll talk of irrigation water. You must be wondering why we are emphasizing on irrigation water. Don't forget, what you eat is produced by the crops when they are irrigated. So let's begin. Groundwater quality criteria or water quality criteria assessment for irrigation water. Most of the time we are worried of few things here: salinity, sodium adsorption ratio, a specific ion toxicity. Now what is this salinity? That is the total dissolved solids in water. How it is going to affect the crops? If this TDS is very high, then the water intake in the root zone will be very less. And so the crops won't grow, they won't yield. And though you apply water, you have no output. Now how do we measure it? You can do it in lab, but the easiest thing to do is you measure electrical conductivity, and there is a relationship that 1 milligram per liter of TDS is roughly equal to 1.56 microsiemens per centimeter of EC at 25 degree centigrade. So how it helps us? Question is, how it helps us? It helps us because we have handheld EC meters. There you just dip it in water and find the electrical conductivity and then convert it into TDS, and you have the TDS value. Most important is that we assess irrigation water based on this electrical conductivity and sodium adsorption ratio on a plot which we will discuss further, that is CS plot, C-S. Now, sodium adsorption ratio. First, why sodium is so important? Because high sodium concentration in the root zone reduces permeability of the soil. And if the permeability of the soil is reduced, there will be less infiltration of water to root zone, and so no crop yield. And this is greatly controlled by sodium ion concentration vis-a-vis Ca and Mg ion concentration. You must keep in mind that when we estimate SAR, all the concentrations are in milli-equivalents per liter. So what is SAR? SAR is sodium adsorption ratio, concentration of Na in milli-equivalents per liter divided by root under concentration of Ca added to concentration of Mg in milli-equivalents per liter divided by 2. So that is SAR. Then what is a specific ion toxicity? Some ions like chloride, sodium, boron, if they are in very high concentration, they harm the crops. Boron is very famous for that, and thus you need to assess the quality of irrigation water so that these ions are in desirable limit. Okay, what is next? You must guess. That is graphical representation of groundwater quality data. You must be wondering, why do we need to do this? Look, the water management is handled at many levels by bureaucrats, technocrats, politicians at panchayat level. Now you need to show your results in the best possible way so that you convince them to manage it prudently. And for that, we have many graphical representation tools. It started with bar graphs, then circular diagrams. You first remember that whenever we do this representation, it is mostly in milli-equivalents per liter. Nowhere it's in ppm. But these bar graphs, circular diagram, they were of use for 1 or 2 samples. What if I want to show to my pradhan that look, there are 9 villages and you have 100 samples? You will make a clumsy bar graph of 100 samples and he might get confused. And thus evolved more holistic approach of using diagrams like trilinear diagram, Durrells diagram, and for irrigation water, CS diagram, C.S. That is, C stands for conductivity, S stands for sodium adsorption ratio. What is trilinear plot? It was given by Hill and Piper together. Not at the same time, at different times, Piper improved upon Hill's diagram to propose this. And here we can only report major ion concentration. You must be wondering, what are these major ions in groundwater? Ca, Mg, Na, K, as far as cations are concerned. Anions, bicarbonate, carbonate, sulfate, and chloride. So what do? You tabulate the data, convert it from ppm to EPM, and then again you find percentage of each cations vis-a-vis total cations present and percentage of each anions vis-a-vis total anions present, and then you plot them on the diagram. Let's see how we do it. Okay, this is the infamous trilinear diagram. If you become a hydrogeologist, this will trouble you for life. Let's have a look. There are two triangles, one on the left, another on the right, and there is a diamond-shaped central area. This triangle on the left is a cation triangle. This is the anion triangle. Look here, we have Ca, Mg, and Na plus K is clubbed in the cations. In anions, we have bicarbonates, and if carbonates are present, they are clubbed with this bicarbonate. We have chloride and sulfates. What did I say earlier? Ca has to be found out as a percentage of summation of Ca, Mg, Na and K. So you have a Ca percentage, you have an Mg percentage, you have Na plus K percentage. Now let's look at this plot here, this dot. So here the counting is like this. This tip of Na plus K is 100% and this all line is 0. So you move like this towards this tip. All this is 0, this is something, this is something, this is something, this is something, and this is 100. Now what is this something? It depends on the number of divisions between 0 and 100. So you have 1, 2, 3, 4, 5 divisions. So this is 20, 40, 60, 80, 100. Similarly, tip of this Mg is 100 and the line opposite is 0. And as you move like this, so this is 0% Mg all along this line, this is 20% Mg, 40% Mg, 60% Mg, 80% Mg, and at this tip it is 100% Mg. So you must, and likewise for Ca. So if I have to plot NaK here, it clearly shows that this was 80% of sodium plus potassium and a very insignificant amount of Ca because it's near to its 0. So I plotted it like this. Likewise, the principle is same in anions. This chloride end, this point is 100%, this line is 0, this all along this line it is 20, all along this line it is 40, 60, 80 and 100. Same way the sulfate end is 100, all along this line is 0, 20, 40, 60, 80 and like on. Now we have plotted another sample here. So you have one cation and one anion plot right now. This is not sensu-strict to one cation. In fact, it represents concentration of Mg, Ca, Na plus K. So we say one sample plot, not one cation plot. And this is one sample plot of the anions. The next step is that you project them as you see here with dotted lines onto the central field and plot here. Now you will ask me, what is use of all this? It gained all its importance by a concept of hydrochemical phases given by Back. It says that major cations and anions in a distinct zone makes a hydrochemical phases. Look here, this is sodium-potassium type. And if it plots here, where I put my hand, In this is chloride facies. Then you will ask me, what is the use of diamond? Diamond gives a synoptic view. So if it plots here, it's something. If it plots here, it is chloride plus sulfate facies. And like that. What is the advantage? You can plot 100 samples here on the cation, 100 on the anion, 100 in the diamond. What will that give to you? Let's say you have one cluster of plots at the bicarbonate, one cluster at the chloride, and similarly, so this is for the first 50 samples, this is for the next 50, first 50, next 50. It says distinctly that the groundwater has two distinct and different phases. One is bicarbonate, one is chloride. It speaks a lot about their origin, the hydrological processes, and so many other things. Okay, that was the trilinear plot, popularly also called as Hill-Piper's plot. Hang on guys, you must understand what is the fun a scientist or academics have. They play, but they don't play with so many things. They play with ideas. And this is what Durrells did. He played with this idea of graphical representation, and he brought out a new plot. Durrells was a Russian scientist. Most of his work couldn't see light because they were in a different language than English. And so it was another scientist who reported Durrells' plot. And there again, you represent the major cations and the major anions. In his extended version, there is some more option of plotting EC, pH, or two more parameters. Let's have a look at the Durrells diagram. Okay, this is a prototype of Durrells diagram. Now look here, the two triangles are same. The one horizontal is the cation triangle, the one vertical is the anion triangle. The processes are same. First you convert ppm to EPM, then find percentage of each cation vis-a-vis summation of total cations. Percentage of each anion vis-a-vis summation of total anions. Plot them similarly, like this magnesium end is 100 and the line opposite is 0, and you go like this 20, 40, 60, 80. So you have 2 points here, and then you project them to a central field. The advantage which Durrells gave was the extended Durrells, which is not shown here, that you can extend this particular square in two directions and then plot two more parameters to give a better holistic view. Now comes the most important for me, and that is graphical representation of irrigation water. Why? Because millions of life depends on this, and we are an agrarian economy. Fortunately, unfortunately, this is not being done at a great level. Now how it is done? The simplest way is that you have a plot which is referred to as conductivity versus sodium adsorption ratio plot. And on this plot, your conductivity is on a logarithmic scale and SAR is on an arithmetic scale, and then you classify the water for irrigation use. Let's understand it in detail with help of the figure. Okay, this is the CS diagram. What is it? You have a horizontal scale, that is x-axis. This is a logarithmic scale. And here you have C1, C2, C3, C4. That is electrical conductivity in micromoles or microsiemens per centimeter. And you have a y-axis where you have sodium adsorption ratio. They have been divided into low, medium, high, very high. That is low conductivity, medium electrical conductivity, and so on. Low sodium adsorption ratio, medium sodium adsorption ratio, and like that. And then the whole central area is divided into so many fields, and each field has been given a name, like this is C1, S1. This is C1 and corresponding is S2. And then if your sample falls here in C1, S1, this is excellent for irrigation. That area will have a rich harvest of crops. If it falls here, C4, H4, that's unsuitable for irrigation. Let's not be pessimistic. Then you have to be rather concerned about the other measures which needs to be adopted to increase the crop productivity in this area. And so you can plot some 100 or 1,000 of samples here and classify suitability of irrigation water. Let's summarize what we learned today. May not be in the same order. We learned about water quality. Every water which occurs subsurface is not your distilled water. It has some baseline concentration, and that comes because of sediment water interaction. And you have total dissolved solids. Besides, you can have some bacteria, some organic things, radioactive substances, and so many other things. Water quality is judged by its desired use for the purpose. Next, we learnt about contamination and pollution. Contamination is adding any substance to groundwater, either through geogenic source or by anthropogenic means. Pollution is when this contamination is beyond the desired or permitted limit. We also came to know how these quality parameters are measured, and more important, how they are reported. They are reported for chemical parameters in milligram per liter, for color in Hagen units, and like that for turbidity and other things. Then we discussed about suitability of this water for drinking purpose vis-a-vis WHO and BIS standard. Then for irrigation purpose, we also discussed that it is salinity, sodium adsorption ratio, and toxicity by ions like boron and sodium, chlorine, etc., chloride. That is more important. In the end, we learned that for graphical representation, we have trilinear plots, Durrells diagram, and CS diagram. Thank you. That's all for the day.